Hola. Estoy muy cansado hoy. No quiero enseñar. ¿Cómo se dice uh, uh, go to sleep? Is it dormir? Dormir es el verbo. ¿Verdad? Ah, gracias. Yo quiero dormir. Uh, 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 yo aprendí muchas cosas en mi clase de español. Ok, empezamos. Entonces, empezamos. All right. Oh, I gotta zoom in. Um, yo toco 1, 2, 3, 4, 5, 6. And then it zooms in the right amount. How do you say 6 times if you do something 6 times? ¿Cómo se dice 6 times en español? Yo hago algo 6 times. Okay, so this is AP1. Hoy es viernes 13. Viernes 13. Ooh. Friday the 13th. No one's going to answer my question about how to say something 6 times. Okay. I guess I better start teaching physics instead of speaking Spanish. Come on, focus for me. Come on, focus. I find that the more things I put in the image, the faster it focuses. It like has more reference points, I think. Okay, so let me just talk really briefly about last time. Last time we were talking about circular motion, and so you have this thing that's moving in a circle of radius r. Uniform circular motion meaning a constant speed. It's not speeding up or slowing down. We learned an equation for the speed in circular motion, which is 2 pi r divided by capital T, which stands for the period, so the time it takes to go around once, And we learned that wherever you are in the circle, the speed is given by this, but the velocity points tangent to the circle. So in this case, there are kind of two tangents to the circle, so it could be going up or down, but this would be something that's going counterclockwise around the circle. Okay. And then we learned an equation for the centripetal acceleration. So recall that centripetal acceleration is acceleration due to purely direction change and not due to change in speed. Okay. So the formula for centripetal acceleration is v squared over r. Or if you prefer to express it in terms of period instead of speed, this would become 4 pi squared r over the period squared. So this is called the centripetal acceleration. Okay. And the reason it's called the centripetal acceleration is because if you work out the math of something moving in a circle, which we do in AP Physics C, you find that the acceleration points in towards the center. So that's what centripetal means. It means center seeking. So wherever you are in the circle, the velocity is always going to point tangent to the circle, and the acceleration is always going to point into the center. Okay? Now, because you are accelerating, Newton's second law is still valid if you are moving in a circle. And so Newton's second law is valid. So F equals ma, but for the acceleration, we plug in the centripetal acceleration, goes into the right-hand side of Newton's second law. And the force that is making you move in a circle is called the centripetal force. And just like the centripetal acceleration, the centripetal force also points in towards the center of the circle. Okay? If it pointed outward, so you might have heard the term centrifugal force, and there is such a thing as a centrifugal force. So centrifugal means away from the center. But the discussion of centrifugal forces is sort of beyond the scope of this course. So we're just going to have centripetal forces that point towards the center. Okay. So we're gonna basically just be doing example problems today. All right. Using Newton's second law and circular motion. So the first two examples that I'm going to do are what I like to call horizontal circles or flat circles. Okay. So these are circles where if you were to look at these circles from a top-down view, they look like this. Okay. If you look at it from a side view, you would see just edge on, right? You would see something going back and forth, edge on. So the center is right here, and you're seeing it kind of loop back and forth. All right. Now, what is significant about flat circles? Well, the significance of flat circles is that you're looking at it from the side, gravity points downward. mg points downward. So the significance of horizontal and flat circles is that gravity is perpendicular to the plane of the circle. Okay, and so what we'll find is that that actually makes the analysis a lot simpler. Okay, so horizontal slash, also known as flat circles, are easier to analyze because gravity, basically that means because gravity is pointing perpendicular to the plane of the circle, gravity is not a centripetal force because it's not pointing towards the center. Okay. Okay. All right, so we're just going to do some examples. So let's say that a cyclist of mass 50 kilograms wishes to navigate a turn of radius, let's say 12 meters. The coefficient of friction. Now, if you have a cyclist, and in general, if you have any vehicle that has wheels on a road, you actually have static friction. Okay, you have static friction. If the vehicle is operating, properly, because kinetic friction would mean that the tire is sliding across the surface. So peeling out, for example, is an example of kinetic friction acting on the tires because the wheel is sliding against the surface of the road. So skidding, drifting, peeling out, these kinds of things are using kinetic friction. But under nominal conditions, you actually have static friction, okay? So I'm going to say the coefficient of static friction, and I should say this is a flat turn, by the way, between the tire and the road is 0.75. How fast can the cyclist navigate the turn without skidding? Because if the cyclist tries to enter the turn too fast, basically the centripetal force will not be big enough. I guess we should talk about what happens if the centripetal force isn't big enough. All right. If the centripetal force isn't big enough to go in a circle of a given size, you will actually start to go in a circle of a greater size. Okay. So basically, you will start to move in a larger circle than you intended. Okay. Now, what would this look like if you were in a bicycle and you started skidding? You would skid and you would slide to the outer edge of the road. Okay. So we're going to start out with Newton's second law, F equals ma. And I want to know how fast. So for the acceleration, I'm not going to use the 4 pi squared r over period squared because that doesn't have speed in it. Okay, so instead I'm going to use the v squared over r because I'm trying to solve for speed. Okay. So I have v squared over r. Now the centripetal force in this case is static friction, and because we are going as fast as we possibly can in this circle, static friction is maxed out. So you might recall from our discussion of friction that friction goes up. Static friction goes up to a maximum value. Okay, and basically, if that's not enough to prevent the object from moving, it will start to move, and then you have kinetic friction. So basically what we're doing, because we're going the maximum possible speed, we are experiencing the maximum static friction. Okay? Now you might recall that the formula for maximum static friction is mu sub s times the normal force. Okay? So instead of doing a new line, I just wrote it over here. Now, I'm going to ask a question of you guys, which is, if you are on a flat surface, what is the normal force equal to? If you are on a flat surface, what is the normal force equal to? And I will wait. Yeah, mg. So it's just the gravitational force. Excellent. So, yeah, if you're on a flat surface that is not moving, your normal force is just the weight force. So I can rewrite Newton's second law. So I have my force is mu sub s mg. Okay, so I've replaced normal force with mg. And then I have mv squared over r on the right-hand side. Mass times acceleration on the right-hand side, force on the left-hand side. One of the things we can see here is that mass is on both sides of the equation, so it cancels out. So even though this was a 50 kilogram cyclist, that had no bearing on how fast the cyclist can navigate the turn. Okay? So we have mu sub s times g equals v squared over r. So now I can start plugging in numbers. The radius of the turn is 12. Gravity is 10, and the coefficient of friction is 0.75. So I multiply both sides by 12, and then I take the square root, and that gets that the maximum speed is equal to 9.5 meters per second. All right, which is around 20 miles per hour. A little more than 20 miles per hour. So, so yeah, if the cyclist enters the turn with more than 9.5 meters per second of speed, then they're going to actually skid, and that could be dangerous. Okay, so this analysis is completely general. It doesn't have to be a cyclist. It could be a car on a freeway, for example. So I want you to type it into the chat if you know the answer. What are some different things that might affect the coefficient of static friction between tire and road? Okay. All right. So and so it's a really interesting question. Like, what should the speed limit be on a road? Okay, so you want to think about a lot of different things. Um, you want to think about the I completely lost my train of thought, but yeah, people put a lot of good responses in there. Yeah, so basically the road conditions, the weather conditions, are determining the coefficient of friction. Okay. Now, when you're deciding the speed limit, you want to think about what is the coefficient of friction, because the coefficient of friction affects how quickly you can stop, and it affects how sharp the turns can be. Okay. Um, so if you have a road with a turn of a given sharpness, um, have you ever gone into a turn and it has a reduced speed limit because it's a particularly sharp turn? So basically, the people who make the speed limits are thinking about equations like this, and they don't want you to skid and fall out of the turn. Another thing to think about is psychology. All right, so even though the maximum speed, the maximum upper limit might be 9.5 meters per second. They might mark it as 8 meters per second because, as we know, if you mark the speed limit at speed V, people usually go 5 or 10 miles per hour above that speed, or maybe even 15 miles per hour above that speed. Okay? It's kind of interesting because in California, I observed that people go 15, maybe even 20 miles per hour above the speed limit, and they don't get tickets usually. Where I grew up in Washington, the cops are much stricter on speed limit. So you could get a ticket for going 5 miles per hour above the speed limit. If you're going 10 miles above the speed limit, like, you're really asking for it in Washington State. So if you ever go to Washington State, make sure you go the speed limit because they will light you up. Another issue is we're just talking about skidding, but the other issue on a turn, if you have something that is like a very tall car, like a truck, then it actually has a roll. It could roll, and that's a whole other issue. So road designers are thinking about, is this car going to skid? Is it going to roll? Now, if you have just a non-truck vehicle, then the danger of rolling is a lot less. Okay. Let's do another example. Let's suppose a spring has stiffness 135 newtons per meter and natural length 0 meters. Okay, so this is like a spring that if you let it go, it literally contracts down to nothing. Okay, that's somewhat unrealistic. All springs have a natural length. It is whirled. So let's say a 5 kilogram mass is attached to the end. And it is whirled in a flat circle with speed 11 meters per second. what is the radius of the circle? So, as you might predict, you could try this at home. If you took a rubber band and you tied something to the end of the rubber band and you whirl the thing in a circle, the faster you whirl the thing, the more that rubber band is going to stretch. Okay. All right. So we're going to start out with Newton's second law. Net force equals ma. Once again, because the speed was given, we are going to use the v squared over r version of the centripetal acceleration. The force, because it's a spring, the force is the elastic force, kx. All right? Now, we have to be a little bit careful here. If you, in the homework, I have a problem where the natural length is not 0, okay? But because, so remember, x represents the distance beyond the natural length. So because the natural length is 0, if you have a circle of radius r and this spring is stretched, then the amount that the spring is stretched is equal to the radius, okay? So for this particular problem, we have kr equals mv squared over r. All right? But in the homework, I think I have a problem where the spring has a natural length that is not 0. So for example, what if you have something going in a circle of radius 1.5 meters, but the natural length of the spring was 1 meter? So how much, if the radius of the circle is 1.5 meters, but the natural length is 1 meter, the extension of the spring is the distance that it increases beyond its natural length, so it will be 0.5 meters, okay? So that's just a heads up for the homework today. So if I rearrange this, I get r squared equals mv squared over k. So now I can plug in numbers. So the mass is 5, the speed is 11, the k value is 135. And then I take the square root of that, and I get the radius of the circle. And I get that the radius is 2.1 meters. Okay. Boom. All right, so that was my discussion of flat circles. Now, actually, an interesting type of physics problem that if you take my AP Physics C class we discuss is a banked turn. So you might have seen, you know, in NASCAR, for example, on the turns, they actually have a slant on the roadway. And what that does is it actually makes the normal force a centripetal force, which allows you to go faster around the turn without skidding. So if you take my AP Physics C class, we will analyze that situation. In fact, we already have in my AP Physics C class. Okay, so now let's talk about so-called vertical circles. Okay, so a vertical circle is one where you're looking at it, okay, and if you look at it from the top view, okay, if you look at it from the top, all you see is the circle edge on because it's vertical. If you look at it from the side, you see the circle, all right? Now, what makes vertical circles more tricky is that we're looking at it from the side. Gravity always points downward. So no matter where you are in the circle, gravity points downward. So if we look at when you're at the bottom of the circle, gravity is actually a centrifugal force. All right. So that this makes it more complicated. Okay. Now we will only analyze vertical circles at the top of the circle or at the bottom. Okay, so we're only going to analyze these vertical circles here or here. If it's somewhere in between the top or the bottom, it gets way more complicated. So this is your first physics class. We're not trying to, go too extreme. All right, so we're going to talk about 3 different scenarios, okay? So let me draw them. All right. Okay, so we've got so we got 3 scenarios here. The first scenario is a car that is at the bottom of a ravine. Okay. Now, how many of you have been in a car and the car, goes over the top of the hill and then it enters a ravine, and at the bottom of the ravine you feel squished into your seat? You probably felt that before. All right. How many of you have been going over the top of a hill in a car and you actually feel lighter at the top of the hill? All right. So we have a car that's at the bottom of a ravine. We've got a car that is at the top of a hill, and then our third scenario is a skateboarder who's doing a loop-de-loop. Okay. All right. Now, if we think about where is the center of the circle in each of these cases, here, in this case, the center of the circle is right here. All right. It's above the car. So the direction of the centripetal acceleration is towards the center of the circle. So I'm going to put a big goofy arrow here, and I'm going to put A in it to represent that the centripetal acceleration is upward in that case. All right. If we look at this case, the center of the circle is down here. All right. Again, if you're moving in a circle, the acceleration points towards the center of the circle. So that's downward. So here, the centripetal acceleration points downward. So I'm going to put a big goofy arrow pointed downward. Here, the center of the circle is right here. So again, the centripetal acceleration points downward to the center of the circle, because here's the person up above the center. All right. So now we got to think about forces. All right. So we just did acceleration. Now we're going to do forces. So I'm going to do a little free body diagram of the forces on the person or on the vehicle in each case, all right? So here we have the weight force is going downward, all right? And the normal force, because the floor or the ground is below the car, the normal force points upward. All right? Now you might be asking the question, well, why did I make a separate arrow for the acceleration? That's because acceleration isn't a force, so it shouldn't be in your free body diagram. So I just gave it a different kind of arrow just to make that clear. All right? If we look at this scenario, we again have the floor below, so that means that the normal force points up, okay? And then the weight force points down, as it always does. All right? Here, we have, once again, the weight force points down, but then for this skateboarder, the floor is above the skateboarder. So that means that the normal force also points down. Okay? The normal force also points down because the normal force points away from the surface and perpendicular to it. Okay? So you got to be careful about that. So these problems are all about getting the right sign for each of these terms. Okay? So I'm going to write net force equals ma for each of these. Newton's second law for each of these scenarios. Okay? So let's do the net force. So the net force is upward force minus downward force, or upward forces minus downward forces. So the net force in this first example, the upward force is normal force. The downward force is mg. So that's my left-hand side of Newton's second law in this case. Here, the upward force is normal force, the downward force is mg, so the net force is normal minus mg. Okay? Type it into the chat if you know what is the expression for the net force in this case where both the normal and the weight force are downward. All right? Now I'm going to do MA. So here, the acceleration points upwards. So the acceleration is a positive number. So I have plus v squared over r, positive v squared over r. Please keep in mind that even though I put a plus sign here, that's just indicating the sign. So this isn't m plus v squared over r. It's m times positive v squared over r. Here, the acceleration points downward. So I have m times the quantity negative v squared over r. No one wants to type in the expression for the net force. Come on, someone can do it. I believe in you. Okay, no one wants to answer it. Okay, fine. The net force in this case, because they're both pointed downward, is going to be minus normal force minus mg. Oh, just in the nick of time. Great job. Okay, very good. And then the acceleration also points downward. So it's going to be negative v squared over r. Okay, so the tricky part about vertical circles is that the signs of each term. Okay, that is 100% the tricky part about vertical circles. So if you can just draw the free body diagram, figure out where the acceleration is, and then just be really careful about the sign of each term, then you'll get the answer correct. All right, that's the tricky part about this. And really, I've given you the three scenarios that, you know, we've done like all possible combinations, essentially. All right, let's do some examples. A car of mass 3,000 kilograms is at the bottom of a ravine of radius 40 meters with speed 50 meters per second. What is the normal force on the car? So for this example, we have a car at the bottom of a ravine. So that's this first example here. So I'm just going to copy Newton's second law down from this. Normal force minus mg equals mv squared over r. So I dropped the positive sign just because. All right. And I'm trying to, so now I can just plug in numbers. Normal force minus mg, so 3,000 times 10, that's going to be 30,000. Okay. Equals m, which is 3,000, times v squared, so 50 squared divided by 40. Okay, so that says that the normal force is equal to 217,500 newtons. Woo-wee! Okay, so let's think for a second about this answer, because this is a crazy answer. So here's the thing. If you had a car that was just sitting on a flat surface and the car had a mass of 3,000 kilograms, its normal force would be 30,000 newtons. It would be mg, 30,000. But because this car is at the bottom of a ravine and it's moving at a very, it has a pretty large speed, 50 meters per second. That's over 100 miles per hour. The car actually feels a normal force not of 30,000, but of 217,000 newtons. So this is what I was talking about. When you're at the bottom of a ravine, you feel smushed into your chair. And the reason you feel smushed into your chair is because the normal force has increased so much when you're at the bottom of that ravine. Okay? So this is just an illustration of that. Comparing the normal force when you're at the bottom of a circle and you're moving quickly to your normal force if you were just standing still on a flat surface. It can be quite a, many times what it was before. In fact, if this was like a bus and you were standing up on the bus, you would probably just crumple. You would literally just your legs would give out and you would just hit the floor really hard. It would be interesting. All right. We'll do one more example. So let's say a skateboarder of mass 40 kilograms does a loop-de-loop of radius, let's say 5 meters. How fast does the skateboarder need to go must the skater go at the top of the loop-de-loop to not fall? Because what would happen if this skateboarder is not going fast enough in the loop-de-loop? So if you're going fast enough, you go woo, woo, like this, all right? But if you're not going fast enough, you might have, if you've ever played with like Matchbox cars and they have loop-de-loops, right? If something is not going fast enough, it'll go woo, splat, and it'll just fall directly out, okay, of the circle, okay? So now here's a key point. I want you to pay attention to this. So if the skater falls out of the loop-de-loop, they have lost contact with the loop-de-loop, with the whatever you would call it, the pipe. It's not a half pipe. Would you call it a full pipe? I don't know. So when you lose contact, okay, this implies that the normal force becomes 0. This is really important. If you lose contact, that means the normal force is 0. Why? Because the normal force is the force of contact between two surfaces. So if you're not in contact, there cannot be a normal force. Okay? So we're looking at this scenario. So we have minus F sub n minus mg equals minus mv squared over r. So I took the negative sign here. This was multiplying by -1. It's not m minus v squared over r. It's m times the quantity negative v squared over r. And I just moved it to the front. Okay? Now, again, losing contact means normal force is 0. Okay? So we have minus mg equals minus mv squared over r. So a couple of things are happening here. The negatives cancel out, and they become positives, and the mass also cancels out. So I gave you the mass, 40 kilograms, but your answer would have been the same if it had been a skateboarder of mass 5 million kilograms, okay? So what we get is g equals v squared over r. So we have 10 equals v squared over the radius is 5 meters. So we get v equals square root of 50. Which is 7.1 meters per second. So if the skateboarder got to the top of this loop-de-loop and was traveling only at 5 meters per second, they're going to fall out of the loop-de-loop and probably hurt themselves, okay? If they're going at, I don't know, 8 meters per second, that's more than enough and they can actually complete the loop-de-loop. All right? So that is my lesson for today, and I will see you in the Zoom room where we will watch Wolfcast.